Hey, welcome back to Fan Mama Physics. In this video, we are going to do questions on standing waves. Okay, standing waves. The questions that I will do in this video will be 7 and 8 from your worksheet. So my computer is not cooperating, so then you can look at this. Oh, there it is. So then you can take a look. This is our worksheet, worksheet 6.9, 7 and 8, and let's begin. I might even fit both 7 and 8 in this video, so we'll try our best. Okay, 7 and 8, explain this observation. I'm just going to do it using words and maybe a diagram. I'm not going to actually write it fully out. Here we go. A source of sound of frequency 2100 hertz is placed at the open end of a tube. Okay, so you got a tube, okay, and we got a sound coming in, okay, okay. The other end of the tube is closed, okay. Powder is sprinkled inside the tube. When the source is turned on, it is observed that the powder collects in heaps at a distance of 8 centimeters apart. So you get a heap here, you get a heap here, you get a heap of stuff, you get a heap of sand, you got a heap of sand. Okay, is that sand? Powder, whatever it is. And this is 8 centimeters apart. Okay, explain this observation. So what is happening here is this has to do with, again, standing waves. So what's going to happen with sound is that it's going to travel through this part of the tube, it's going to hit the other side, reflect back on itself, and it's going to reflect back on itself and interfere with itself as it's coming back, producing standing waves inside this tube. And for standing waves, it looks like this. It looks like little circle blobs, essentially. So it looks like this, and it comes back and reflects. So it makes these little blobs. Now, these blobs have points on them. For example, the parts where the wave is maximally displaced, this is called an antinode. Antinode, okay. These ones, the ones that have no displacement relative to the equilibrium position, these ones are called nodes, okay. And for the wave there is, so imagine you're walking through this standing wave here. Imagine you're a little person and you're walking through it, and this standing wave just continues to oscillate up and down. So what that does is it kind of flips like this. Okay, if I'm walking through here, I'm going to hear no sound. I'm going to hear maximum sound, no sound, maximum sound, no sound, maximum sound, no sound, etc. So when there's no sound, there's not a lot of vibration happening. So here's the question. If there are sand heaps that are over here, would that represent a lot of vibration on the sand in these particles, or no, very little vibration? And if you think little vibration, you're definitely correct. So where these points here would be where the nodes are going to be. So a node's going to be here, okay, a node's going to be here, and it will continue to go like this, and it's probably going to end up there because it's a fixed end. So imagine you have a rope on a string. If you tie one end down, that's exactly where it's going to be. It's going to be tied down to the closed end. But for an open end, it's going to be able to just fan out like this, because it's, imagine you have an open end on the string can just flap back and forth. So that's what the representation of this would look like. And that's what the standing wave would look like in this tube. This is going to be important for us to solve the next part of the question, which is use this information to estimate the speed of sound. Okay, so first of all, we do know a few things. We know that the frequency given to us is 2100 hertz. We also know the different distance between two nodes. And two nodes, if you take a look at in terms of relation with the wavelength, from node to node is at exactly 1/2 of a wavelength. So for the whole wavelength, we need to double the distance from node to node. So our wavelength here is going to be 8 centimeters times 2, which is 16 centimeters or 0.16 meters. And if we want to find the speed of sound, if we know the wavelength of this of the wave that's going inside the tube, we know the frequency, we can use it to figure out the speed of sound. So this is going to be frequency times lambda, or 2010 hertz times 0.16 meters. So if you just want to put that into the calculator, then that's going to give you 336 meters per second, and that's going to round to about 340 meters per second for the speed of sound in question 7B, when the computer cooperates. There it is. Okay. Okay, so that is question 7. Oof, that was pretty fast. Guess what? We're going to do question 8 in the same video. 8. A tube with both ends open is placed inside a container of water. What a nasty way to word this one. So when it says it's an open end, that's when it before was placed in water. After it's placed in water, if you consider the medium, you have air, okay? Air to air, this is open. Okay, this is open. But the bottom, because you have air to water, this end is actually closed. So this one is fixed end. There's a fixed end there. So you have an open closed pipe for this case. When a tuning fork above the tube is sounded, a loud sound comes out of the tube. Woo! The shortest length of the column of air for which this happens is L. Okay, so that's the length there. The frequency of the tuning fork is 486 hertz, and the speed of sound is 340 meters per second. So we're given the frequency and we're given the speed of sound. We can use that to figure out wavelength. So if you absolutely have no idea what to do in this question, you can just go ahead and figure out the wavelength. So I'm going to draw question 8 maybe again down over here. But first of all, I am going to figure out the wavelength. The wave equation is velocity equals to frequency times lambda, in which lambda is going to be our speed divided by frequency. Our wave speed is 340 meters per second. Our frequency is 486 hertz. Okay, so that's going to give us, divided by 486, 0.6995. Wow, that's like close to 0.7. Meters. Okay, so we know the wavelength now, where you need to figure out the length. Okay, so when you do this problem, you need to be fully fluent in drawing all of the diagrams associated with open open, close close, and close open pipes. You need to know how to draw those diagrams very well. First of all, we want to figure out the shortest length. Okay, so the large sound was heard when the length was the shortest, meaning we're going to fit the least number of wavelengths as possible inside this distance L in the tube. So if we take a look at your closed open pipes, you have the first possibility, which is this guy over here, in which the first standing wave pattern looks like this. And then you have subsequent ones where it looks like this. But no matter what, this end will always be open, so the mouth of the wave, kind of the antinodes are going to be there. You're always going to have a node there. But then if you have fit another wave in here, it's going to kind of look like this, in which you have a node, and the antinodes at the open ends. Okay? But in this case, we want the we want the shortest length. Okay, so meaning we're going to try to fit we need to fit less wavelengths inside this tube. So it's not going to be our orange case. It's probably going to be our blue case, where we fit this one. In fact, is actually a quarter of a wavelength here. So what we need to do is, we know that this length is exactly a quarter of a wavelength, and if you don't believe me, you try to continue this on. So this is just going up to the peak, going up to the trough, and it has to come down to the trough for half a wavelength. So this is a quarter of a wavelength. So our wavelength, we know, is 0.699. So to put this all in, we get 1/4 times 0.699 and whatever that is. This is going to be this one divided by 4 equals to 0.17 meters for the shortest possible length needed to make that to make the constructive interference happen. Okay, and there it is. Answer's right there. Okay. B. Predict the least distance by which the tube must be raised for another loud sound to be heard from the tube when the same tuning fork is sounding. So when we have the same tuning fork, it means we still use the same wavelength because we took the speed of sound divided by the frequency of that tuning fork, which gave us the wavelength. So this is exactly what we need. We need the same wavelength, 0.699 meters. But now we have, imagine we're taking that tube and we're moving it up. Meaning we're going to extend the length of this tube. So it's going to be longer than it was before. Okay. So it's going to be like maybe here or something. Now, before the extension, this used to be the length. And our wave kind of looks like this for the standing wave. But now we have an extra bit of the tube, which then again, if we have a longer tube, the same standing wave pattern is going to occur. And for a standing wave inside an open closed end, on the closed end, there will always be a node. So if I had to redraw this for the next one, what we're going to happen is we're going to get another node down here, in which the middle is going to be our antinode. So that's going to be the shape of our standing wave with an extended length. And the extended length is only larger by one of those blobs. And the blob is from node to node, which is exactly half a wavelength increase in distance. Okay, so what's the question? It wants the new length? Is that what it is? We want to predict the least distance must be raised. Okay, so what we want to find is we want to find this distance here. Okay, that's the distance of which the tube has to be raised in order for us to get a standing wave pattern again. So since this is half a wavelength from node to node, then we know that since our wavelength is 0.6995 or whatever that is, we just have to multiply this one by 2 to get now multiply by 2. This is the whole wave. We need to divide this by 2 to get half of the wavelength, which is equivalent to the increase in distance in the tubing. Okay, so that means we're going to take this guy and we're going to divide by 2, which is going to give us 0.35 meters. And that's exactly the answer to this question too. Okay, so here we go. So that was question 9. So notice this question requires you to know the shape of your standing waves in all of these different pipes really well for you to be able to solve the problem. And notice every time that you kind of extend the pipe, or it really doesn't matter if you're going from one harmonic to the next harmonic, it's going up basically by a node or an antinode from the, well, it's essentially it's going up by half a wavelength. So half a wavelength gets you the next harmonic, which then, if you know the wavelength, you will know exactly how much you need to extend the length of the tube by. Okay, so those were the 2 questions. Let's see if I can put it on one page. Anyways, I hope you got something out of these examples. I thank you for watching, and Fat Mama Physics signing out.